Hi, thanks very much for attending this presentation. So I'm going to start today a little bit talking about real-time data, the problems that it can have, the problems that it has processing it, the problem that we get. And we also look at a little bit the problems that are caused by the data growth that we're seeing as a result of smartphones, IoT. And the idea here is we're going to see how Infinispan, which is an in-memory data grid from Red Hat, can help you with these real-time data processing requirements or data analytics. And the best way to show these things is to see a live demo. So I'm going to be doing a bit of live coding so you get a feel for how these things work. And I'm going to be using things like Vertex and OpenShift as well. So it's going to be a bit of cloud. I've already been introduced, so I don't want to repeat myself really, but I want to find out about yourself. So just so that I get an idea, how many of you are Java developers? Okay. The others, what do you do? Like Node.js, JavaScript developers? Okay. There's going to be a lot of Java here, but as I'll say, a lot of the things that I do here with Java can be done with other languages because we support JavaScript and other languages. So of those that have used Java, how many of you use Java 8? Okay. Oh, very few. Okay. How many of you know about Infinispan? Oh, yeah. Okay. How many of you know about Hibernate? Okay. How many of you use second-level cache for Hibernate? Okay, very few. Okay. All right, just to get an idea. So the objective of today is, if you can see it very well, is to look at how we can use Infinispan to build infrastructure to store, search, and process near-time real data and calculate analytics. Why is it difficult? First of all, dealing with real-time data, streaming data, is a unique challenge. You can do a lot of real-time processing with batching or offline analytics. But for a lot of businesses, a delay of a few seconds can mean the difference between keeping or losing a customer, or it can mean the difference between increased liquidity or fraud, or even risk losing money directly. And even a few delays can be the difference between a problem in manufacturing versus being detected by the system. So in essence, for some systems, real-time processing can be quite a challenge. On the other hand, we've got a problem that is not going to go away. The amount of data being generated is just growing exponentially. We've got things like smartphones, IoT, which are basically producing a lot of data. The question is, how are we going to go about analyzing it? Okay, how do we approach this? So the solution that we've been working on for quite a few years is what we call in-memory data grids. In-memory data grids can help you with this real-time data and offline analytics as well. So what is an in-memory data grid? An in-memory data grid is, in essence, a way to manage distributed in-memory. The idea is that you've got a bunch of servers that are all connected to each other in a kind of peer-to-peer communication style. This means that there is no kind of master slaves anywhere. All the nodes are equals to each other. So there's no single bottleneck or no single point of failure. And these kind of setups are designed to run on any type of hardware. So that means in the servers you have in your company, in a cloud, anywhere. So Infinispan, in essence, is an in-memory data grid. What it offers extreme performance thanks to the storing the data in memory. It's also linearly scalable thanks to smart data distribution techniques we use, where we can configure it to keep n copies of the data. So it means no matter if we have 10 or 100 nodes, it works the same way. The idea is that each of the nodes in a grid keeps a subset of the data. So by doing that, you kind of get implicit data parallelism, because data is kind of spread around the cluster, and you can kind of potentially run things in parallel. If you want, you can also back it with a persistent store. So you can back it with a database, a file system, cloud, Cassandra, MongoDB, etc. And also, it's accessible from any type of application. So that means that you can kind of enable transparent sharing of your application data. And we've got connectors available for Java, Node.js, C, C++, .NET, etc. So, in its simplest form, an in-memory data grid such as Infinispan can be used to boost your performance. The idea here is using it as a second-level cache, or as a cache. For example, if you're using Hibernate, maybe you want to cache the data coming from your database, and then so that next time you don't need to go to the database, you retrieve it from memory. Other examples would be if you're storing metadata or lookup information or temporary data. But you can also store it like for data that might be hard to compute, so maybe data that is coming from scientific applications or complex graph calculations. You can also use Infinispan as a NoSQL database. Here, Infinispan offers you a simple, flexible way of storing a variety type of data without the constraints of a fixed data model. And you can configure it so that it runs with transactions. And you can kind of use it as your own primary store, but you can also have it as persisted. So you have it with a file system, a database behind the scenes. So this enables you to explore fast access to data, and then being able to then run parallel workloads on your distributed your distributed data grid. So it means you can kind of shift workloads into them, run them in parallel, and then bring them together. I know you can also have queries, so you can run rich queries, not just key value store, and then it's elastic, and you can recover from failures as well. So it's quite powerful. You can also use Infinispan as an event broker. Here, what we're doing is we are supporting an event-driven computation. Here, the idea is that I am putting some data into my grid, and then I'm creating some kind of listeners which react to the changes happening in the backend. So you could use it for real-time computation, like I was talking before, and that can help you with many cases. It can help you with fraud detection, risk management, I don't know, like dashboards, all sorts. The idea here is to bring kind of the processing or kind of the data closer to where the data needs to be processed, rather than having to fetch it manually. And the final use case that we had is when you want to use Infinispan for data analytics. In its most simple form, you can run some analytics already using Infinispan's distributed Java Streams API. You can also do more complex analytics if you use Spark or Hadoop. And you can actually use Spark and Hadoop backed by Infinispan, so backed by your in-memory data grid. Regardless of which of the options you use, the idea is that you take advantage of the inherent data parallelism available in a data grid to run your analytics. Now, in terms of what type of applications would I use Infinispan on? All sorts. We can go web, e-commerce applications. You could use Infinispan to store your HTTP sessions, user-specific information. You could store in-flight shopping carts, information about your customers, so that if the nodes go down, they can carry on shopping. You can also use it as a alternative or to reduce the load on legacy data stores or databases. So the idea is you could take product catalogs that you might have in databases and storing in the data grid, or you could use for caching. Other areas where the Infinispan is used a lot is in telecommunications. You can use the data grid for keeping information about billings, prepay, customer information, call routine, session information. You could keep SMS content. You could run your notifications through the data grid as well. And you can also use in travel. So if you work in travel, you can use it for showing aggregated flight pricing or availability of flights, for example, to store that data. Also in finance, again, per user portfolio data. You could use aggregator ticket streams and pass it on to algorithmic trading, risk detection, fraud detection. And you're going to be using defense in the defense sector. So if you have a network of sensors and you want to process your data coming from those sensors and detect if there's a threat. So the use cases are multiple. All sorts of applications can benefit from Infinispan. Now, the talk today, I'm going to be focusing mostly on these two things. The event broker, which is going to help us with the real-time use case, and the data analytics that is going to help us with the data growth. So for the event broker, one of the key features that Infinispan contains is something we call continuous query. Now, for retrieving data from Infinispan, there are multiple APIs available. You've got key value store, so if you pass the key, you get the value. You've got querying API. But if we want to address this kind of real-time use case, we need something a bit more advanced. And the idea is that the continuous query API enables you to be reactive to data changes. It's essentially an extension to the query API, which allows you to, for your application to receive entries that currently match a query. But on top of that, if there are new data that it's stored into Infinispan that matches that query, you will get notified with this new data. On the other side as well, if data is removed from Infinispan, then you will get listener callbacks saying, hey, this data is not part of your results set anymore. So this might sound a bit complex. So the best way to understand is to show you a demo. Okay? So we've built a demo based around Swiss transport, and specifically rail transport, about Swiss rail transport. And here you see a little bit what the domain that we are going to work with today. So we've got trains, which are trains. So they got an ID, they got a type, or if it's an intercity train, regional train. Then we've got stations, so Basel, Zurich, Geneva. And then we store geolocation information, etc. Now, the interesting part is that for each station, there's going to be one station board. A station board shows you what trains are coming up. And then it shows you what we call stops. So these are each individual entry in this station board is going to be, we call it a stop. So this is like, this train is going to arrive at this platform at this time. And it also is going to tell us if it's delayed. Now, the reason I'm talking about delays is because we're going to be working a lot about train delays. We're going to see what happens. So the two demos I'm going to show you today are going to run on top of OpenShift. OpenShift, for those who might not know, is Red Hat Platform as a Service environment, which allows you to quickly develop, host, and scale applications. It can be run in a public environment, or you can run it in your own company. And it supports applications running in multiple languages, Ruby, JavaScript, Python, and Java. And this is what I'm going to be focusing today. It's based on Docker for the images, and underneath uses Kubernetes for the orchestration. On top of that, we're going to be using Vertex. Vertex is going to be a little bit our glue between our client application and the data grid. What is Vertex? Vertex is essentially a toolkit for building reactive applications on the JVM. It's essentially event-driven and non-blocking, which means that your application can handle a lot of concurrency using a very small number of threads. It's also polyglot, so that means you can interact with it from multiple languages. Again, Java, JavaScript, Ceylon, Ruby, Scala, anything. Now, oops, that doesn't show very well. Okay. So to help you understand a little bit the demo, I've prepared some diagrams which are now up here. Hello? 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 Hey. So I prepared some diagrams which should appear a bit better, but I'm sorry. I'm just going to go around and explain, okay? So all this part that you see here is going to run on OpenShift. This part here is separate, okay? With that in mind, what we've got two deployments. On one side, we've got the data grid, which is formed of 3 pods. Basically, we scale it down up to 3 pods. So we've got 3 instances of Infinispan. They are configured with a replication of 2 nodes. So if one of them goes down, we can continue processing. In the middle, we've got a little load balancer. And on this side, we've got a real-time deployment. This here is running 3 vertex verticals. Verticals are a bit like actors or like little units of processing. The first one here is the injector. This is an injector. This is going to be injecting data into the Infinispan. What data are we going to be injecting for this first demo? It's going to be going around. We've got a file where we've captured about 2 hours worth of station board data around the country. And it's basically going to be pushing that into the data grid. Okay? Then what we're going to have here is we're going to have a vertical that sets a continuous query. Now, what are we going to try to do with the continuous query? We're going to try to find, of all the station boards that we have in the system, which belong to all the country, which are, I want to get, in the end, a dashboard that shows me all the delayed trains that are happening around the country. So here we're going to have a continuous query that says, get me all the station boards which have, as data gets loaded, send me a notification whenever there is a train delayed. And then what are we going to do with the train delayed? We're going to push it via a SOC.js bridge over to this HTTP vertical here. The idea is then that here I'm going to have a JavaFX application, so like a GUI, that is going to receive these events via WebSockets. Is that understood? I'm really sorry about the diagram. So really find better colors. Okay. So, right. So let's demo this. Right. Yeah. Okay. Second. Yeah. Okay. Right. So the first thing that I want to show you here is hold on. Oops. Right. Let me clean this. Right. So the first thing that I'm going to show you is I'm going to run the FX application as is right now, so that you see a little bit. I'll see it a little bit. So here we are, the application. At the moment, it doesn't show anything. It doesn't show anything because the code is incomplete. The idea of this talk is to kind of do a bit of live coding so that you see that how things work. Okay. So right now, the idea is that we want to have this dashboard where it shows me all the delayed trains as they're going through. Now, this particular live coding, or for this one, is going to be focusing on this continuous query vertical here. So this is the vertical that is going to create the continuous query. One of the things I want to note for now is this. We've got the data model we're using, or we're storing in the grid, is a station-to-station board mapping. So for each station, we're getting at one given point, what does the station board look like? So if we look at the station board, we've got essentially 2 elements. Timestamp, which is the last time that we updated the station board, and the list of entries, so each of the entries of the station board. Now, one of the key things about the stop is in the stop there is something called delay minutes. So it's an attribute of the stop. So what we're going to do is we're going to create a query that says, get me all the station boards where there is at least one of the stops that is delayed. Okay? So this is what we need to essentially build in this query here. So how do we do that? We need to do query factory from. We want to do a station board class. Then having, what we need to do is to say of the station board delay minute we want to say give me the station boards where at least one entry is delayed. So how do we know it's delayed? Is because the delay minutes is greater than 0. Okay, so then we build it. Okay, so we have our query. The next thing that we need to do is create our listener. So the listener is already scaffolded here. So what I need to do is, if there is any entry and trains that are delayed, they're going to be in this list. So what I want to do is I'm going to take the entries, I'm going to stream them, and what I'm going to do is filter them. The reason is because when I say get me the station board that contains at least one entry, one stop that is delayed, then obviously there might be other trains that are on time. So what I'm trying to do here is basically say, okay, just give me those that are just delayed. Okay, and then what am I going to do with each of the with each of the trains that is delayed? I'm just gonna basically push it. Let's stop, and I'm gonna be pushing it to. Oops. I'm going to be publish it. So I'm going to send it through that SockJS bridge that I was talking about earlier. Okay? Okay. Now, there's one final thing I need to do. So I've got the query and the listener. So what I need to do next, I need to put those two together. So I need to do continuous query at continuous query, listener, query, and the listener. That's it. Okay? So now I have my continuous query vertical complete. The next thing I need to do is I need to redeploy it. I need to basically get the cloud to basically run it again. So there are multiple ways in which you can kind of push changes to OpenShift. But one of the ones I use, I normally like to allow to kind of build first the package and then use a kind of a Docker file to push it. Kind of works really well for my case. But there are other ways to do it. You can use Fabricate Maven plugin. There's a source to build kind of feature as well in OpenShift. And the next thing I'm going to do is I'm going to so I've built the package, now I need to push it. So with OC start build, I'm just going to be pushing it over to OpenShift. Okay, so now it's pushed. What I need to do is I need to just rerun my client application. So if the demo gods have been nice to the demo gods, then they should be appearing here. So we start to see. So we start to see the first train delays. We've got train going from Badische Bahnhof to Basel SBB is delayed 3 minutes. We've got Solothurn to Zurich, 31 minutes delay. Wow, that's a big delay. So you see that trains get delayed in Switzerland as well. Okay, no, it's not just in the UK. So this is what I want to show you a little bit, how you can use continuous query with Vertex and to kind of push some real life data. And yeah, it's very cool, I think. Right, so this is what I wanted to show you for this particular demo. So we're gonna continue with our talk. The arrangements. Okay, oops. Right, so in the next part, I'm going to be focusing on data analytics. How can I use Infinispan to do some data analytics? Now, as I said, there are two primary possibilities for doing analytics within memory data grids, like with Infinispan. The first is you can use Hadoop or Spark APIs combined with an Infinispan backend. This gives you kind of the advanced data analytics APIs exposed by Spark or Hadoop with kind of an in-memory data grid. So it's kind of combining the two. Spark and Hadoop have a very proven record, and they work really well. But the problem is that Spark and Hadoop are their own beasts. They require resource management. They have their own clustering. So you have to do a lot of kind of messaging to get that working and to maintain that. So I would say Spark and Hadoop are very powerful, but then you should see whether there are any simpler ways to achieve that. And one of the things that we came up with in Infinispan is we decided it would be nice to use the Java 8 Streams API to run data analytics. So what we did in Infinispan 8, we took the Java Streams API and we made it run in a distributed environment. And the reason we wanted to do that is because with Infinispan, the data is already partitioned. It's already distributed. So if the Streams API really offers us a nice, easy way to kind of distribute our computations and then bring them together. Now, when I was raising earlier, when I asked you to raise a hand, you said a lot of you maybe didn't know we're not using Java 8 Streams. So I wanted to, I've already, in my previous code, I kind of briefly showed you a little bit Java 8 Streams. So I just wanted to kind of explain you a bit more so that you understand. So the idea behind Java Streams is that it gives you a way to kind of ship through elements of a source and applying that kind of a pipeline of computation. So the idea is to kind of have 0 to n intermediate operations, and then those don't get invoked until you call a final operation. Final operation would be something like reducing all the computation into one, or collecting all the computation. The cool thing with Java 8 is that it takes advantage of lambda expressions. So it means that you have a very expressive language for defining computations in a way that seems pretty neat. One of the things with the streams is that the elements can only be visited once. So if you need to revisit them again, you're going to have to start from scratch. So what we did with Infinispan is have the ability to get all these lambda expressions that you see here, have them a way to kind of spread them to other nodes. So the idea is that instead of having the processing bring all the data and do it locally in one node, say, okay, the data stays where it is. What we ship around is the function or the lambda. So it makes it for a very, very neat approach. And it's obviously been used before in technologies like Hadoop. So for the next demo that I'm going to run today, it's going to still be about train systems, Swiss train rail system. And the question that we're trying to answer is the following. What is the time of the day when there is the biggest ratio of delayed trains? Now, this is a question for you. Who thinks, so I want to do a little raise of hands. Who thinks that the biggest ratio of delayed trains is at 7 o'clock in the morning? Rush hour, morning rush hour. How many thinks that? No one? One person? What about evening rush hour? Who thinks that's the time? Okay. What about midday? What about midnight? Only one, two. Okay. All right. So this is the question that we're trying to answer. What is the time of the day where we get more delayed trains? Okay. And it's a non-trivial question. It might surprise you. So again, I've got a demo and I've got some diagrams to show you, which doesn't show well here. So let me use the magic pointer to help here. Right. Hello. Hola. Right. So again, here we've got OpenShift, which runs up to here. Here in the front end, we're going to have my laptop, and that's going to be running Jupyter. Has anyone heard of Jupyter? No? Jupyter? Jupyter is a data science tool. It's kind of like a notebook where you can write Python or Node.js code, and it can allow you to plot things and show really cool diagrams and everything. It's very neat. I really like it. Should definitely give a go. Right, so we've got that in the front. So that Jupyter is going to show us it's going to plot. Create us a plot, so at midnight, between midnight and 1, 1 and 2, 3 and 4. So we're going to see what the ratio of delayed trains throughout the day. So what we're going to have again, we're going to have here in a backend, we're going to have a data grid configuration. Here, this is pretty much the same that we saw earlier. The only difference is that we here have, which you can't see very well, but we've deployed a server task. Okay, a server task is like a remote procedure call that you can call on Infinispan. And then that one is, we're basically going to call one of the nodes, it doesn't matter which one, and in that call we're going to run our distributed streams. So we're going to run our distributed streams to calculate this data. And as I said before, we only need to run one node because this node then in turn is going to take care of shipping the lambdas to the other nodes so that I can do the distribution. So here what we have is a little server task, and then we've got something in the middle, which is just a load balancer. Again, it uses replication key here as well, like 2 nodes, just like the other one. And here in the analytics area, what we have 2 verticals. One, an injector. This injector basically takes 3 weeks worth of data from the station boards, which is about, I think it's 2.5 million entries. And it basically on a startup, is stored into the data grid. Then we've got the Jupyter notebook. It's going to basically make a RESTful call to our analytics vertical. This analytics vertical is the one that is going to invoke the server task. Okay? And then that server task will land in one of the nodes. We don't care really about it. Okay? So the idea is to use server tasks that are deployed into the data grid to then run distributed streams there and then calculate this, find the answer to this question. So let's see this in action. Right. Where are you, pointer? Amazing. Okay. Right. So we're gonna close this for now, and then. Okay. So we've closed what we had, and then we're gonna go on to our next demo. So just so that you see, this is what Jupyter looks like. So Jupyter is like a little notebook that you run locally, and then it enables you to kind of it uses some Python APIs that are very popular with data scientists. And it kind of allows us to kind of write little pieces of code, execute them, and etc., and then plot. So let's see what it shows us for now. For now, we're just going to go through the different steps. So we're going to see that's the URL we're going to get. That's the URL exposed by our OpenShift environment. And then we're going to just request a URL, see what happens. For now, we just get 0. That's because this server task that I'm going to live code is not ready yet. So for now, we're getting no results. So let's go to the code. What are we interested in developing here? I'm going to focus on the distributed streams part, because that's the part that I want to show you how to do calculations for. Now, there's a couple of interesting things here. One, the data that we store in the cache here, we kind of store it in a historic way. So we've got an ID for each of those lines in a station board, and we're storing about 2-point-something million word entries of those. Okay, so what we need to do is we need to shift through those entries. Now, to find out which time of the day we have the most delayed trains, we have to create 2 things. We need to create 2 maps. One, for each time of the day, so between midnight and 1, 1 and 2, 3 and 4, how many trains are going through the Swiss rail system? And then we also need to figure out, per hour, how many of those trains are delayed. And then getting those 2 pieces of information, we'll be able to plot it. So how do we do that? Well, we first, obviously, we're focusing on the values of our cache or of our data grid, which is the stops, and then we're going to call a stream. And then what we do really here is very simple. We need to collect. Now, the thing, if you use Java API, there's something we can call collectors group by to do this kind of like per hour separation. But the problem is the collectors grouping by returns an object that is non-serializable. And as I said before, one of the key features of distributed streams is that the functions are going to be distributed. So the way we work around it is we can, for collectors only, we can do it lazily. So what we can do here is to say collectors grouping by. Where are we grouped by? We're going to group, for each stop, we're going to get hours of the day for the stop's departure. Yeah, and then for collectors count. Okay, so what we're doing here is saying, okay, we know that the collector is not serializable, but we just do it lazily. So what we're doing, we're sending a function around that lazily is going to create these collectors in each of the nodes. Okay? Now, is that more or less understood?
Serialize, is that a Infinispan function?
Huh?
Serialize, is that an Infinispan function or the?
This is a function. Really, it goes on to cache collector, serializable collector. It's kind of a trick to kind of force it to kind of be. Yep.
How would it be different from just casting the lambda to serializable lambda?
It's essentially the same, but then what happens is there's a trick. If the parameter is already a serializable supplier, you don't need to do any casting. It already casts for you. So this is a bit neater rather than you having to do the cast yourself. So the other thing that we need to figure out is the delayed trains per hour. Again, we need to do a similar thing that we did before, but here we need to filter, okay, of all those stops, which ones are delayed. And one thing that you've noticed here, this lambda here, I don't need to serialize it. It already, the filter method that we have here is already dealing with it. This is a serializable predicate, so we just need to pass it as such. We don't need to do any tricks. And then what we need to do is we need to collect again, and then what we need to do is serialize again, serialize, grouping by, and then we need to group by the same things we did again, the stop and counting. Okay? So that gives us the two maps of how many trains per hour are running through the system, how many of those are delayed. What do we do with those two? We just basically essentially send them back to the client. The client, which as I said before, is going to be, it goes through a vertex vertical and eventually gets to the front end, which is the Jupyter. Now, the next thing I need to do is I need to kind of load back this server task into our data grid. So the way to do it, one way to do it, which we are still experimenting a little bit with these things, is we need to go to the analytics here, and then what we do is we first rebuild our task, and then once we've built it, one of the things we do, in this demo, I'm just going for a simple host path. Okay, I'm telling the data grid, you can fetch new tasks from this folder. Okay, so it's a little bit, it's a bit not very cloud-like, but it just works for this particular case. So now we just need to get back to our notebook. So what we do, we kind of go through the different operations. So now we invoked here the one that is going to get us the analytics. Takes a few seconds, and then we get 48. 48, I'm just here showing you the analytics size so that I know myself that it actually did something. Now, on to the big question. The next question basically takes the analytics that it got and it just plots them. And we see that, oops. 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 Okay. Okay. How am I? Okay. So I think you start to see it there. The time of the day where you get the biggest ratio of delayed trains in Switzerland is 2 o'clock in the morning. Huh. Does anyone know why? Or anyone care to guess why that is?
It's a percentage of the number of trains are really less than the same.
Well, we're calculating ratios.
Yeah, but it's a percentage, so the number of trains which are there, they're all delayed. That's the current.
Yeah, but why would they be delayed?
There was a sleeping.
No. There is a reason why they are delayed. Once I arrived at Geneva Airport and I managed to get the last connection of the day, the last train. But to get to where I wanted to go, I need to stop in Lausanne. So this was the last train I could take to get to my final destination. And I had to stop in Lausanne. This first train was delayed. And I was panicking. I was like, oh my God, I'm going to arrive in Lausanne. I'm going to be stuck in Lausanne. I'm not going to be able to do it. What happens in Switzerland is the last connections of the day, if they are delayed, they wait for each other. So I was able, when I arrived in Lausanne, I was pleasantly surprised that even though my train was delayed, the other one was waiting for us. So it means that whenever there is one delay, it affects the entire system. So it means it's a ripple effect. One moment there is one delay, everything else is delayed. That's the reason. And you also see it around midnight. So midnight, 1 o'clock, 2 o'clock. So as the last connections of the train happen, you get a lot of this thing. And it's even better. I mean, and you see, if you just so that you see the number of trains or the number of things we're talking about. If you execute the next one after, we see starting to see what the results are like. So at 2 o'clock in the morning, we've got about 2,000 trains running. Of those, 321 are delayed. But look at 6 o'clock, we got 5 o'clock, 113,000, of which only 5,000 are delayed. Amazing. I think this is great. So this is what I had to show you today. To go back to my presentation. Oops. So just to go back to the initial objective of this talk. So our objective today was to show you how Infinispan-based infrastructure could handle real-time data and do analytics, interesting analytics, not just word counts. And we saw that obviously handling real-time data can be challenging. And then that there is an enormous amount of data being generated, whether it's by transport, by sensor data, by a smartphone. So it's important that we learn how to maximize or how to do cool stuff with it. And then we saw how continuous query, which is a feature of Infinispan, can help you with real-time data processing. And finally, we saw how even though Spark and Hadoop are really powerful, you can do quite a few neat things with Infinispan distributed streams. And I wanted to thank these amazing people who let me use those cool, some of the cool icons that I've shown today. And I leave you with this slide, which is probably the most important one. All the code and the data that I've used for the demo is public and available in that GitHub repository over there. So there are instructions on how to run this, how the demo is structured, how to run it, etc. What the requirements are to run it, etc. So if this is of interest to you guys, I would highly recommend that you go there and have a look, and then you play with it. And hopefully as well, there might be a video of this, if the video is working well, so you'll be able to see it, to go through it. If you want to find out, in terms of the repo, there's a branch, early 17, so that's the one for this particular talk. If you want to find out more about Infinispan, go to infinispan.org. OpenShift, you can find everything about it on openshift.com. And finally, if you want to find out more about Vertex, obviously this talk was not focused on Vertex, so I haven't really shown much of the code. There is code there, but obviously there's only so much I can talk about in this talk. But if you want to find out more about it, go to vertex.io. If you have any comments, please, Twitter, comment. It's nice to hear whether it's good feedback, bad feedback. I don't mind.